accidentally turned off the stream. Yeah, let's see, it should be back up now. Yeah, here we go. Okay, so pardon me, I hit the wrong button and turned off the stream. Now, if you wanted to use Windows 11, I made a download you can use, but it's not worth any points, and I don't encourage many students to do it, but if a couple students would do it and let me know if it works, I might gain enough confidence that this is okay, that I can actually make a version of it with all the tools, and then you can use Windows 11 instead of Windows 10. I tried that twice before, and both times it was so horrible that it was damaging students' machines, and I quit using it. That stuff about blackbirds in the chat, I don't know. I think it's like that. I mean, yes, crows are smart. You're right. Some birds are smart. Crows are smart, parrots are smart, but a lot of birds are not very smart at all. Anyway, so if you want to use this Windows 10, you can download it from this class. If you go to 126 and you go to your projects, I put it at the bottom of the Windows VM. I said not recommended because not only does it not have any of the tools installed, but also I'm not very sure that it's going to be usable because earlier versions of Windows 11 have been horrible, but this is Microsoft's official version. So hopefully they have removed the terrible problems that we were having. And so you can download this thing, 12 gigs, just unzip it, and it's a virtual machine ready to play in VMware. Here's the login, and here's the disk encryption key, which is supposed to be stored automatically in it, so it won't ask, but if it does ask, that's what it is. And this is full Windows 11 with all the features because it has a virtual TPM2. And I know it runs in VMware Fusion, because that's what I'm using here, and according to VMware documentation, it will run in VMware Player 14 and above. So a free product on Windows will be able to play it. Yeah. All right. Anyway, so feel free to download it and play with this way if you want to, or make your own with the links that I had earlier. Anyway, but today's primary topic is assembly code. Now, you don't need to learn a lot of assembly code to do the simpler kinds of malware analysis, but I do encourage you to learn some assembly language. So it's all extra credit. There's quite a lot of extra credit here, and there's another, you can put flags, and there's a scoreboard here. See anybody on it yet? Nobody yet, just me testing it, and mine doesn't show up. Anyway, so you need a Linux machine to do this. I did not figure out how to do it on Windows, although there are Windows assembly code things. So once you have a Linux virtual machine, either a local one or a cloud one, then you can install an assembler. And so the one we're using is NASM. There are various ones, but NASM is the one that we need here. That's the one I chose just because I'm following a tutorial. There's a very nice tutorial we'll get to. And so let's talk about assembly code. So if I nano hello, come on. Nano is the text editor I like to use. It's an old, simple text editor in a non-graphical environment. I like to run my servers headless, and I'm used to this from doing exploits, where you get a command line shell on a server. What's the difference between this assembler here in Unix and Windows Assembly? Nothing much. The Windows Assembly uses different software, and a couple of commands are different. But basically, they're very much the same because you're really down at the level of the hardware here. You're below the operating system, really. So the only difference is the environment you see on the screen when you're creating it. The actual code is essentially identical. But I'm just used to doing the Unix one, so that's what I did, and that's what that tutorial did. So here we are in assembly. You see I have sections. The text section, and this should be pretty familiar with you from all the PE stuff we did. There's a text section and a data section. The data section is very simple. It just has a series of bytes. You can give a name to a variable, and you can say, I'm going to have a series of bytes. DB is a series of bytes. And then you just can put characters, and it will turn them into bytes, 1 byte per character. So this is hello world. Now I can define a variable length, which is a label, and this equals the current location minus the address of message. So this is going to be the length of that string in bytes. It's going to be the difference between the start of this string, which is the address of H, and the address of the next byte after the end of this. So that's going to be the length of it. Yes, that's exactly right. That's the point of this. This is just going to look like the assembly you saw in IDA Pro and in Ollie. That's right, exactly. Anyway, so that's the data section. And here's the text section. You define a label that is global, which tells it where it starts. And then you just have machine language instructions, which are just like we've had in so many other programs. So you put now what's going on here is that all the action is being done by syscalls. int 80. int 80 is a syscall. That's an interrupt. Remember, int 3 is a break to put you back in the debugger. int 80 is a syscall. And all you do when you're programming a computer in an operating system is you keep calling the kernel to do the work. Because remember, your code is in user mode, and you can't touch any of the hardware. So you can't even print anything on the screen. That's hardware. You are not allowed to directly send anything to the screen. All you can do is ask the kernel to do that for you. And the way you call the kernel is with interrupts. So it switches from user mode to kernel mode and runs it. And when it goes there, it then looks in these registers to find out what you want to do. And so for, the EAX determines which kernel method you're calling. 4 is print, 1 is exit. So when I'm done with the program, I exit by just having 1 and calling exit. I don't need any other parameters. Here, EAX is 4 for print. EBX is the device number, which is 1, which is standard out. This is a pointer to the start of the message, and this is the length of the message. So the registers are used to hold the parameters, and the int is what calls the kernel. And that's it. And all you do is find the kernel call that does what you want and figure out how to set up the parameters and call it. And this is essentially what almost all programming is. As we talked about before, in Windows, normal Windows code, you would be calling Windows API calls. And in, all right. And if you were programming something on Facebook, you'd be doing Facebook API calls. And here we're doing kernel mode, kernel calls. So that's the game. And so here's the explanation. And here's a little chart of system calls. There's a whole page with all of them, but here's all the ones we need. Exit, read, and write. We're not even going to use fork. So 1, 3, and 4 are enough to do everything we're doing, but there are a bunch of others. So, all right, so here's a syscall 4. Syswrite shows you this. So it is the pointer to the buffer and the size, and the FD here is the file handler. So anyway, that's the game here. And here it tells you where to put them. EAX gets this number, EBX gets that number, ECX and EDX, and on you go. Anyone try the prof? I don't have the zoom turned on. I could turn it on if you want it, but I normally only turn it on later so people can share their screen. Would the numbers such as 1 or 4 be in a header file? You could define them as symbolic constants. That's the kind of thing Microsoft might like to do. But I don't know how you include a header file in assembly code. There may be some way to do that. I've seen that in C, but I don't know how to do it in assembler. This is very simple assembler I'm teaching you. There are certainly more advanced ones. Anyway, that's the story here. And so when you want to run this thing, you have to first assemble it with NASM, and that will turn it into object code, hello.o, and then you have to load it. And I'm making 32-bit assembly because that's mostly what we've been doing. So if I go to here, I save this. By the way, Control X, Y, Enter is how you save it. And then these commands here. All right, so this does the assembly down to object code. This loads the object code, and it turns it into 32-bit assembler. You could have different kinds of assembler, but I'm choosing to use 32-bit as the most familiar to us, and that runs it, and it prints hello world. And we didn't tell it to print a carriage return line feed at the end, so it stops right here. Now, we could add the carriage return line feed to it. In fact, let's do that. That's a good thing to do. So if I go back to Nano, if I want to add carriage return line feed, it is 10 and 13. 10 is line feed and 13 is carriage return, or else it's the other way. So I can just add them there, and since I calculated the length, this will automatically notice that it's too longer. So let's try that. Now I compile that with NASM and load, and then run. Oops, that edited it. There. Now it puts a carriage return line feed at the end, so it's prettier. Anyway, all right. So that's simple enough to print. That's basically hello world. And now, if you want to learn more, there's a nice tutorial here that will actually explain how a lot of this works. I'm going to open it in another tab. All right. And these tutorials point things are great. I've got several whole CTFs based on what you learn here. And this explains the basic syntax and the registers and the system calls. So here's the syntax. Programs have data, BSS, and text. You've seen what the data is. That's where you declare variables and constants. The BSS, you can declare variables that will be stored on the stack. And the text section is where the code is. And here's the system calls. Linux system calls, they explain how the registers are used. Here's the ones we did, 1 and 4. 1 to exit, and 4 to print, which is called write, to write to the screen. And here's a few of them. The first 6 syscalls. And there's an example here. So, it's very nice stuff. This one here, you can read and enter, and it will read a number and it'll echo it back to you. So they use the read and the write syscall. So this is a print with 4. That'll print some kind of prompt. Then you're going to read and store user input. So that's going to be 3 to read. So you have to give it the length of how many bytes to read and a pointer to the number to store it in. So you can read. So that's the story. And there's some questions here and some flags you can answer to get points for learning about some things about the theory. And then you can get back to the hands-on. So now that you know how to do reading and writing, you can do quite a few things just with that. And here, you can do a head request to my server. If you can correctly format a head request, which is 3 lines of code, head, HTTP 1.1, host, and a carriage return line feed at the end, then you'll pipe it to a connection to one of my servers, and it will give you a response that contains a flag. One thing that I noticed is you have to have the 10 and 13 as carriage return line feed. You have to have them in the right order. I was very surprised. I just threw this together and ran it, and it gave me not a 200 OK, but some kind of error saying the thing was misconfigured. The Apache server is so picky, you can't have line feeds carriage return if it wants carriage return line feed. So be aware of that. And so then you can make a get and so on. You can, and you see there's an example here of what it should be. Here you have log in with the administrator and password, and you have to have the user agent correct, and then you'll see a flag. And then you can start doing brute force attacks, where you try various values out of a list and loop through them to try various values until you find the right way to get in, and so on. And there's more. Here's ASCII, for example. Here you can, this program will read and write. It's just like that sample they saw. It'll read a word and then repeat the word back to you. And here, you're going to get something that takes 2-digit numbers, terminates with 00, and it turns them into ASCII. 65 is capital A, 66 is capital B. So you're going to have to figure out how to take 2 characters and do arithmetic to count up to the total and turn it back into printable letters. So anyway, that's the sort of thing. There's some challenges of that type going up in difficulty here. And, if you're interested in learning a bit of assembler, this will teach you quite a bit of assembly and get started. And you can put flags on here and get a scoreboard up there. So there were some students that were doing this in other previous classes, and I saved the old scores here. So you can let my grader know if you already earned some points from before. But there's quite a lot of points here, hundreds of points if you want them. Anyway, that's what I wanted to show you today, and I'll stick around just to answer any questions. I'm not going to lecture any more from the book today. Assembly makes you see C is much easier, COBOL is much easier, but they're all pretty simple. I saw Caitlin just got a Commodore 64, and man, I got $800 in 1982 for a assembly language program I wrote then that was a kaleidoscope on the screen. And that was back in the really early days. That processor ran at half of 1 megahertz and did 8 bits processing, so it was so that you really had to write an assembler. And assembly was much simpler then, but it's not really that different. Assembly code is a useful skill. As you've seen, if you want to analyze malware or anything, learning assembly is still good. You know, Steve Gibson, that makes the Security Now podcast, he made SpinRite, which fixes broken hard drives, and he writes everything in assembler. He's an expert at assembler. He knows how to make high-quality assembler with the right style and everything. How many points do you need to get an A? Well, I haven't figured it out yet. It's usually something like 500 or 600. So this is quite a lot. Yeah. I mean, there's tons of extra credit. That's why the only stuff I required is the stuff that doesn't say extra, and you can just do other things instead if you like. I'll get him, Steve Gibson, grc.com, I think. He's one of the old experts in computing. Should be GRC, Gibson Research. There you are, grc.com. That's it. And it's Security Now is the podcast, which I highly recommend. It's on my homepage. Go to this one, Security Now. This is probably the most famous security podcast in the world. That is Steve Gibson, and I guess that's him too. And the point is, he's one of the old standbys, and this show is every week, and it's very interesting. Yeah, that's Leo Laporte. Steve is the guy that cartoon. This is Leo. Okay. Anyway, these two guys. Yeah, this is Steve over here. Anyway, the point is, they make a podcast every week, and it is very interesting if you're interested in technical security stuff. And among other things, he writes everything in assembler. Doesn't bother with any other language at all, which is saying certain purists do. So it's a very, very good podcast. I highly recommend it. It's the number one I recommend for my students. It's security at an interesting technical level. It's been going for like 15 years. It was one of the earliest podcasts. Extremely popular. Yeah, CyberWire is good too. Yeah, there's a lot of good ones. Yeah, I like Prof G and Pivot. There's a lot of them. I sometimes even listen to A16Z, which is in Darknet Diaries is good. Yeah. Anyway, I think I'm going to stop this recording, and I'll just stick around to answer questions.